this month has been fun because it's sort of been Local Heroes Month. Being able to bring in Jay Baldwin and Don Aiken and letting you get a chance to meet the crazy Bill Holliva down there. These are all local folks that, as far as I'm concerned, are local heroes. And today we kind of have the fourth installment of Local Heroes. And that's Keith Marchando. Keith's been here now, we were just reminiscing, for 11 years, is that what?
A little more than 11.
A little more than 11, but anyway, he's been here for a while. And Keith and I have co-conspired on a couple of different things over the years. But in particular, I really want to give Keith credit for something that he's not going to speak about today, but that's the photovoltaic system that's up at the Fairfield Osborne Preserve. I got this crazy idea of having that place run off of PVs because we didn't want to run power lines all the way up to the preserve. You can imagine if you've been up there, that windy road, and to put in big transmission lines and all that was going to be expensive and not really consistent with the mission of the preserve. So we came up with this other idea, which was providing all the electricity for the education center and the residents up there with PVs. So we got some donations from alumni. One of the people that was sitting in the chairs that you're in here, not exactly, but in the Energy Forum in the past, a guy named Chris Freitas, who was working for Trace Engineering, came up with a nice, big, sweet inverter as a donation. So those of you who are working down the road, make a lot of money or have access to a lot of cool technology, we have expectations, right? So anyway, we got a nice Trace inverter donated, and we got some money and some donations here and there. And more than anything, we found somebody that got it on campus that renewables was a good idea and knew what it took to actually put together a standalone photovoltaic system. So if you've been up to the preserve, you see the polycrystal arrays up there that are hooked up to the inverter and the battery bank and all that stuff. And this guy right here really engineered the whole process, figured out what tools we needed, what equipment we needed, what conduit we needed, and all that stuff, got it ordered, got it installed, and it's been running and a big success. So he's been interested in all sorts of things related to energy. I know when he was a college student way back when, he was involved in sort of the political side of energy, but more recently as a professional here at Sonoma State, he's been very much interested in supporting new visions for campus. And that's certainly something that we're going to hear about today. Learn more about Keith's work. He's been responsible for the first major PV installation at Sonoma State University, which was actually out at the Fairfield Osborne Preserve. And then also helped Sasha and the rest of us here at Armando to get the PV system that's on this building up and running as well. But anyway, Keith's main huge contribution now, though, is really been getting the campus as a whole to look at how can you really economically, that'll be a key message today, how can you economically be saving a lot of energy through efficiency technologies and also supplying a fair amount of that through renewable energies, in this case photovoltaic. He's here to tell us the story of Salazar Hall, which is really quite spectacular. Any of the magic away from what he's going to be able to tell you about, but it's a huge success, really a model for other institutions around not only the state but the country. He's already getting significant communication from other campuses and other people and recognition from other professional organizations about the work that he's done. So people besides just us here on campus that are learning about Keith's work are awarding him literally for his good deeds and his insightful engineering. So he's technically a project energy engineer on campus. He works for what's called capital planning, design, and construction. But he's also just a really fine human being who's got a crusty sense of humor, but a good sense of humor, despite the fact that he's been working for the California State University system for a long time. And I'm really delighted to have him as our sort of last installment of Local Heroes to present to you today. So would you join me in giving a warm round of applause for Keith Marchando?
Thank you. I'll be real honest with you. I'm an engineer. I don't know how to do what I'm about to do, how to present anything to you. I work in a real analytical world with facts and figures and things, and my friends Rocky and Sasha have talked me into this. So here we go. This is something Rocky came up with, and you teach a class on photography, 360-degree photography, and this will take you around the roof of Salazar, showing you the indirect direct evaporative cooling units as well as the photovoltaic array up there. I have another picture of it myself in the PowerPoint slideshow. Now let me figure out how to get out of Rocky's pictures and get on with it. Salazar Hall, as you people might know, was originally our library. And it started out as a 120,000 square foot building housing the library. I should preface this by telling you when I came to Sonoma State for the first time in 1970, it was half the current size that it was, if any of you saw it, as you see it now as a physical structure. I was here for a couple of years back then after the war and came here and then left and went back out into society. And when I came back again in '91, the building was twice that size. This campus has always been kind of near and dear to my heart. I came here and wanted to, apply my professional expertise in areas which I had developed over a long time with interests other than sit behind a desk and do just mundane, take it out of the book and apply it. We took, oops, I guess I'm on the wrong page. Yeah, I got to start it. Sorry.
Got a slideshow up on your menu.
That'll work. So here's a little clearer picture of what we've done. On top of Salazar Hall is 75 kW peak AC. I know you learned a lot about peak DC, but in my financial world, DC doesn't matter. What matters is AC, because that's what I'm truly comparing its output to relative to what I'm offsetting on the grid with it. There are 726,000 CFM indirect, direct, evaporative cooled units up there. These units have chill water coils in them only because it had never been done before on this campus, and I wasn't about to take a chance on a possible failure of the indirect direct to be able to carry these structures. By calculations, there were 36 hours a year where the indirect direct evaporative processes could not do the cooling that was required. With my luck, that would have been Larry Schlereth's office and my career right then and there, the days it didn't work. So we chose to make sure we were covered. Oops. Indirect direct evaporative, as you see here, is a direct spray air-to-air heat exchanger. It's called a heat pipe. An evaporative cooling takes place in the return airstream. Direct evaporative cooling takes place in the supply airstream. Referenced up there are the two chapters in the ASHRAE, current ASHRAEs, fundamentals and engineering manuals. If you're interested, you can read more and see how these processes work. This is the heat pipe. This is the indirect process. You have a tube that is filled with refrigerant held at a vacuum, and it sits in the return and supply air streams. I maybe should explain one thing I forgot to mention. These are 100% outside air handlers. This building, every amount of air that goes into the building, a similar amount leaves the building. No air is recycled within this building. And later we'll get into some of the ramifications. I think I covered them towards the end of my presentation about what we're finding out about this environment we're creating. So what takes place is you actually get a transfer of heat, takes place with this pipe that is being spray wetted, and it is, as this process works, doing the primary cooling of the supply air stream. It's a single space. Oh, did I go the wrong way, guys? Let's find out. Now, psychometrics. Across the bottom of this is temperatures. The lines falling through the graph are percentages of humidity. As we increase the humidity, we decrease the temperature. Okay? This is a talk for another day. This is something, if you've taken the classes they teach on that cover this, you'll be aware of it. It's a subject that you could spend hours.
We do this next fall in thermal energy management.
Right. Okay, so indirect evaporative cooler with sprayed wetted heat pipe, 100% outside air is your supplied. You will see that what we do is we do a sensible cooling process, lowering the temperature of the airstream without adding any humidity to it. We're taking advantage of the temperature difference that we do with the refrigerant in an evacuated condition, evaporating and condensing within a tube. Heat is taken out of the outside air and is transferred to the return air side, and 100% of the return air is exhausted. Now, in these air handlers, I have two stages of direct evaporative. One of them is I use for cooling, an economizer cycle, and a humidity control of the building. Comfort is a perception in temperature. If you can elevate a relative humidity to a certain comfort perceived level in the winter, I've been capable of operating this building at reduced temperatures. I'm operating this building in the 67 to 68 degree range with a relative humidity running anywhere from 36 to 51%. Your normal building on this campus is run at 74 degrees, and the relative humidity is not even considered. So it takes higher temperatures to give the occupant the perception of warmth. I have a mandate from the governor, and the chancellor's office that says I will not heat above 68 degrees. Well, that's the mandate. They allow us to go higher because of the discomfort that is perceived when the temperatures are lower. So I've been able to meet that energy requirement that you'll see in 2005 Title 24 about buildings by employing this. The second stage is an 8-inch media. We use that only during the cooling cycles. Direct evaporative, as I said, is a wet bulb process. It adds humidity and, again, lowers the temperature. Now, we operate, here's the combined process. We operate within the current ASHRAE humidity control window. ASHRAE produces an area of temperature and humidity that is employed in buildings, and there are two discrete envelopes on the psychometric chart that we choose to operate in. And this building is capable of pushing into those envelopes the outer reaches of it, maintaining the spaces with the least amount of energy consumed. This has been one of the benefits of having a multiple process. The indirect and direct is a two-stage, as it says, with sprayed wetted heat pipes. You get, the benefit of both processes here. Now, this will show you some of the analytical work we've done. Direct evaporative cooling extends the economizer hours. Economizer hours are times when no mechanical cooling is used, only ventilation from outside air is used. Well, if we can supply to our spaces air through a higher outside temperature by taking advantage of the direct evaporative process, that reduces the amount of mechanical cooling we need, and that is known as ton hours of refrigeration. San Francisco, if mechanical cooling is required on a conventional system for 4011-7, the percentage of time that we eliminate the need for mechanical cooling with direct evaporative cooling and can maintain the air quantities in the ASHRAE envelope or window is 47% by employing this technology. I need to tell you that this is not your grandfather's swamp cooler we're talking about here. Okay? This is highly monitored, highly modulated control. And as you see, we can get 90% saturation efficiency. Okay? Here's a chart. When you look at it, that will explain more. DEC reduces this load in Sacramento by 46.7 relative to conventional. You can see where you actually can take a condition when it's 70 degrees outside and you have a space calling for cooling. And after DEC alone, you can have it to 59 and be pumping it into the building. And then mechanical cooling can take it down the other way, part. And if I'm not mistaken, you notice that there are 91 hours in Sacramento where cooling is needed when full DEC control is used. Now, when you use both of these processes together, the indirect direct, what you start from is a lower temperature. So here you're at that same 70 degrees. You're now at 61 after the indirect process, and with direct you reduce it to what is needed, 55 degree supply air, without mechanical cooling. These are just passive fans operating. Okay, now let's talk about Sonoma State and Salazar. Salazar, right currently now, I have nearly 1 year of good analytical data. This data is showing that the building is saving $45,000 a year in energy coming from the combination of the photovoltaics and the indirect direct evaporative. How it's doing that is we're not operating a chiller to provide cooling to the building.
Is that on a square foot basis?
That's 120,000 square feet. Okay. No, it's not actually. It's on a design basis and a square foot basis, watts per square foot, all things considered.
But is that 45,000 including depreciation for what it costs to start up?
I'll give it all up. It's all here. Okay, let me. let me go with this. And the avoided electrical demand. Okay. With the 75 kW system that generates 113,000 a year, we're looking at a 17% factor on the PV system. Okay, here's an interesting slide. And I'll tell you that this is my nemesis. Originally, what I set out to do at Salazar was, if you were familiar with it in the early 90s or later 90s, it came up that the state of California's answer to the energy crisis was going to be a mandatory 25% energy consumptive at all state facilities. When they called you on the phone, you were to instantaneously reduce your load by 25%. That's a very realistic and attainable figure if you have the ability to control that load. So I set out to take it one step further, and that was to say, if the fans in the building were providing ventilation through this process system, and I had to cut them down 25% instantly from what their full load capacity to provide for the space was, what would I have to have in an alternative energy form operating on the roof so that I would never see a peak demand increase for the operation of this building? Well, that was the premise that I started from. Here's the reality. What we have is a profile of the power on July 22nd, 2003, which was the hottest year we had, or day we had during this time. And somehow I'll get temperature laid across this for us. And you'll see the bell curve of the production of the PV. Between the two black vertical lines are peak energy time for this campus. The blue line is the HVAC load. Now, it may not mean a lot, but 59 kW to do 120,000 square feet is pretty fantastic. And what I've got is I've got a period of time where the PV is not capable of carrying 100% of the HVAC load of the Salazar building. There's a little slice there, two little slices. And my problem is, yes, I'm producing more power than the HVAC requires, but I'm still leaving us out suspect for a peak demand charge for a 1 hour or less window. So I didn't do too bad reducing it by 25% if I covered much more than it was doing. So here we go. The PV array is sized for coincidence with demand. Problem, not all load during the PM peak is offset. Some demand during high rate peak remains. So what could we have done? Hindsight's 20/20. Knowing what we know, we probably, I looked at increasing the array and it didn't life cycle. We could have massaged the system, the panels, put them up on racks and tilted them more towards the west to garner more power during the late afternoon hours. Or we could have used the tracking system. Of these three, if I had to do it again, I would do the tilted modules on a rack. If the aesthetics people, which at that time weren't buying in, I think they will buy now. I think now with this success, I'll be able to you know, they will consider photovoltaic panels not such an eyesore, not such a, to them. You know, there's this great southwest facing, you know, screen that they put up there to hide the air handlers. I mean, I wanted to hang panels on them, and I was bluntly told no. These were beautifully southwestern facing surfaces. I could have probably gotten another 6 kW up there, 7 kW. No, couldn't do it. Had to go with the flat panels. Well, that's okay. We've done that. Now it's on to Darwin and the Rec Center. Knowing how the equipment will actually behave as compared to specs. Predicting building performance. Thermal mass as compared to models. This is another situation that we encountered. When you design a building, you take the engineering that's in the building, the watts per square foot of demand, and you have to match that to an HVAC component. And it requires you to do as close to sizing as you can. Professional engineer today cannot stamp a set of drawings knowing that it's conceivable that the amount of cooling or heating he provided for the space will leave him liable. So what you get is the answer to that in today's engineering world is variable volume systems. And so with a 100% outside air system, it's even more advantageous to you because then you can always make up for the occupant requirement of 15 CFM of outside air per person in the space. So we came with a design for Salazar. We put 7 identical air handlers on the roof of 26,000 CFM. So where we are operating today is these air handlers run during peak loaded condition at about 13,000. There's an unexplained phenomena that has taken place in this building. It's one of the things I'm going to strive to do in the next 10 years is to truly quantify what thermal mass represents in a building such as Salazar Hall. You know, there is no empirical data. There isn't any to be factored in to the engineering basis upon which you say, if my walls are, if my glazing is, I can then factor in that I will take advantage of that through the economizing processes and be able to cool the mass to a point where my later in the day period of time, I won't need 26,000. I actually could say, with a good, safe engineering factor, I need 15,000.
Doesn't that data exist for residences? Or is this a fundamentally different problem?
It's a fundamentally different problem when you get to this magnitude. There is not a modeling program out there that will allow you to model thermal mass into a building. I'm looking forward to being able to find that modeling program that says if I take an average construction steel frame building and I build X number of cubic feet of thermal mass and allow it to be an exposed surface within the building, what impact on the HVAC does that have to the space? Because I think it's there. We've proven it here in the ETC, and I've proven it in Salazar. This building is under study, Salazar, with LBNL. They have been taking empirical data. They've been taking 600 points of data out of this building. It's going through Davis Energy, and we're going to have a report promised to us by the end of June of what we have done here. We're it's a laboratory. As far as I'm concerned, when I get done with that, it's time for Sasha and Rocky to take it and use it as a tool. Use it as a tool to take you there and show you. And by then, I'll have this fine empirical analytical data that I'm going to need. And then maybe I'll re-challenge people to come look at the thermal mass component of this. I already have an agreement with someone at LBL to come do a EH&S study.
LBL?
Lawrence Livermore Berkeley Lab.
EH&S?
Environmental health and safety. All right. Okay, so let me continue here, and I'll get on to a couple of let me go back to that one. Sorry. By the implementation of in excess of 50% of outside air into buildings in the ventilation stream, it has been proven per employee $400 a year in reduced cost to the employer. This is a study done by William Fisk of Lawrence Livermore Berkeley. He's looking for a location. I have gotten a buy-in from the administration here to allow him to come in, go through. They have the ability to provide to him, unassignable amounts of data from which he can use. The occupants of this building came out of the modulars located that have been torn down and thrown away. Let me think. They came out of the lower first floor of Stevenson Hall, the predominant number of them. Some came out of Darwin. So we have a really good mixed group of people to say if you reduce their sick time by 4 days a year by having them in this building that's operating at 100% outside air, you have no possibility of contaminants being left in the airstream for people coming in sick and contaminating everyone else with the airstream, because it comes in, it goes out. Okay. As you saw, indirect evaporative can save 40% as compared to conventional mechanical refrigeration. The combination of direct and indirect evaporative is saving 100% of the cooling energy. I floated a gamble to myself. I commissioned this building and finished commissioning it in October. I closed the chill water valves coming to the building from the central distributed system, took the valve handles off. I had them under my desk until about a month ago, which I threw them in the garbage can. I have proven with this, at this site and at this location, that this building requires no mechanical cooling. Now, I need to be very firm and say that that's Rohnert Park, California, the Salazar Hall building. And when I get done studying this building, I'll explain to you why the thermal mass is the one driving all of this. It has to be. This building doesn't see what I call a flywheel effect, where in the late afternoons this building sees no increased cooling load, because by then I'm economizing, taking advantage of the Sonoma County environment, which is inherently cool. I operate the fans in this building from 4 o'clock in the morning until right at midnight, when the custodial crew is gone. I'm capable of maintaining the space. I've run the space down into 68 degree. I try to maintain 68 in the building, winter and or summer, which all the mass in the building is there. The airstream in the building is 55 degrees when it's pre-cooling or economizing. I take advantage of the direct and indirect. What this building offers is a situation where in a normal building, what you would have is you'd have economizing dampers that are set to a minimum outside air requirement for the occupants, so many CFM per person in the space. Well, this building doesn't have that constraint. This building is always 100% outside air.
I have to nod to Sasha here and say that she did teach us this, and I should know this, but could you once again just briefly explain what an economizer does?
An economizer brings cool outside air into a building, okay, to cool the heat that is in the building itself. Instead of using a mechanical process to
So if your outside air is cooler than
inside air, run it through. Right. Yeah.
Okay.
Okay.
And it seems like, a no-brainer that every air conditioning system should do that, but it's a testimony to the way our culture thinks about energy that we
Right.
have for years built air conditioners that don't even do that.
Right.
So that we have to invent a special name, economizer, for the thing that says, well, geez, instead of refrigerating the airplane, you just bring in the cold outside air that you already got.
Yeah. Okay. Economizing cycle, it's normally called when dealing with a building system. All right, so this goes on to explain. On a peak cooling day, PV output exceeds that of the cooling requirement during most of the on-peak hours in midday. But that's that little slice of the pie I was talking about. That little, if you had to do it again, what would you do different? Armed with the knowledge we have today, I'd have picked the panels up and tilted them to the west. And that way I could have covered 100% of it. Yes.
You're on a direct access building region, right, with the utility here?
We have third party.
Okay. Is there a time of use schedule with that?
It's always time. Yeah, you don't get away with it.
So Keith, would you just touch on that idea for a second? Because time of use is so important, I think, also in the economics of this.
Yeah, well, time of use is set and regulated that from June 1, from noon, okay, we have three levels. We have an off-peak, a part peak, and a peak. Okay? And then, coincident with the peak period of time is a demand charge. So the three different time frames have a different value. And the demand charge comes when you exceed your previous month's average. So if in the previous month you consumed X, and then all of a sudden during the following month you have X running along and you fire up 1,200-ton piece of equipment, well, you've now set a Y. Okay? Now you'll be charged that whole month at that Y level. So I have seen, I do not manage the energy budget for this campus, but I have seen in documentation where demand charges has exceeded commodities here. And that is, something I'm out to end. It's load profile. It all has to do about load profile. What do you look like to those 6 wires going out to the street? Right here on Sonoma State. I'm employed these processes at the recreation center that we did. I'm in the process of employing these processes in a Darwin remodel. We're a Labs for the 21st Century partner with the EPA and Lawrence Livermore Berkeley, and it's lead for labs. It's evolving into that for the designs we're doing there. PG&E's involved. We're going to build, as Salazar has proven to be, we're going to build a laboratory building that is as good an energy efficient laboratory as can be safely built for the inhabitants of science. There you go. All right, where are we at? That's the end. what would I like to say to you? I'd like to say that it's a laboratory, and it will be. It's answered a lot of questions, and it's raised even more of what can be done without mechanical cooling in specific environments. I developed a program to analyze the applicability of this at all 23 of the CSU campuses. In my spare time, what I'm doing is converting bin weather data so that I can enter it into the program, so that I can run it and try and sell this whole concept of this type of cooling to the CSU and get it to be one of the bases. We're in the process of meeting. A lot of focus and study groups are going on about energy efficiency and sustainability, and I think this is going to be one of the big ones. I think this will help us a lot. Okay.
When you were discussing the load profile thing,
Right.
It would seem to me that that whole structure is what is allowing this madness to continue.
I have no control over that. I have to live in it.
When you talk to those guys,
I have to live in it.
how can you even do that with a straight face?
I have to live in it. That when you play poker, the object's to win.
You just have a bigger gun.
No.
Did you have to do anything to the building envelope in Salazar to make this whole thing work, or is that pretty much set?
Well, Loi Glazing, dual pane Loi Glazing, has a white reflective roof, T5 lighting, increased daylighting, lighting control. Let me go on. There's a lot of things going on in Salazar besides the indirect direct evaporative. What? It's tight. All new windows, all new doors. It was all covered. Yeah. Yes.
What about heating? Do you recirculate the air for heating? Or is it separate heating system?
No, it's Vav Reheat. And you know, I'm capable of putting 66 degrees to those VAVs with a 30%, 40% return. I do a warm-up at 4 o'clock in the morning. I'll warm this thing up. I'll close the building down, warm it up, and by the time 7 o'clock's hit, I'm 100% out.
But you do recirculate air during the heating system?
During the morning warm-up only. Yeah. That's been running about 30 minutes. It's amazing. It's, again, the mass. You never let the mass get too cold at night. So, you know, we run different warm-up profiles. The building operates it as like a cool-down profile for the summer. For the shoulder months, we have about a medium profile we run, you know. And in the winter, we keep the profile warmer. And it's a lot of controls. It really is.
So it changes heat from the day to the night?
Yes, through the night. Yes.
Presumably this wouldn't work in humid environments.
It does not work in humid environments. I was born in Pennsylvania, raised in Coral Gables, Florida, attended the University of Miami. 1963. They're going to build Turkey Q nuclear reactor. A bunch of aspiring engineering students. How are we going to cover that? What's the biggest energy load in South Florida? Air conditioning. I can't even remember what a kilowatt-hour electricity cost back then, but heat pipes didn't pay either. I can share with you a little economics if you'd like.
I was just curious, did you look at heat pump technology at all in all of this?
What is the what is the median ambient winter temperature in Sonoma County?
55.
Nighttime.
45.
Where does a heat pump thermodynamics cut out? 45. Doesn't make sense. Sonoma County, Rohnert Park, Santa Rosa. Does not make sense. Once you instigate an electric resistive heating element with a heat pump, it's gone.
The so-called auxiliary.
Yes, heat strip. Now, I'm pursuing ground source heat pumps, but I haven't found the need for them after I found this. Yes?
Can you use the indirect direct evaporative cooling in a residence, or is that...
I'm involved with a group funded by the Public Utilities Commission and California Energy Commission in developing a unit called HIPAC. A little history about the Environmental Technology Center. Davis Energy Group was at that time working on developing an IDAC unit of the size sufficient to fill that hole and that hole. I happen to be working, and unfortunately, what happened is the economies of scale didn't prove to be that they could produce it and sell it where it would be a financially good thing to do. So they had problems. They pulled away from the process. Well, some more funding became available 4 years ago for the development of a 5 to 10 ton light commercial air handler used employing these technologies. And we're actively pursuing it. It's still, there are 2 in production right now. One's in, and they are on test. One's in Sacramento, the other's in Davis, sitting on top of light commercial buildings, running. And, you know, this is newer technology. 3 to 5 years of testing will prove whether it was a viable alternative. Along with that, we're looking at the 3, 4, and 5 ton market to see if we can bring this technology down. And hopefully we'll be able to do it. A larger residence, 7 to 10 ton, maybe. It would be a viable alternative.
I ran into a doctor at a green material showcase who had what he called a new kind of air conditioning, and what he basically did, it was a vac cooler. He cooled the air down, and then he dehumidified it, which was the problem. And he said he was going to put it on the market, you know, next year or something, and I never heard anything. Have you heard anything about that?
No, I can't see where you would, what you would use as a dehumidification process that wouldn't require just as much, you know, transfer of energy and consumption of energy. Okay, let me, yeah.
On the heating side,
Yes.
is your heat source, is that gas fired?
Yes, it comes out of a distributed system here on campus. We distribute it at 260 at 100 pounds, and we heat exchange it down in the buildings to 180 degrees distributed. And oh yeah, there's a central boiler plant here on campus. Okay, what did we face when we looked at designing Salazar? Well, Salazar was going to require 414 tons by design. And our central distributed chill water system did not have the capacity to provide for that. So what we did is we looked at what the cost would be to improve our central distributed system at $1,200 a ton. Took that against what the ad for employing indirect direct evaporative cooling at Salazar would be. And we instantly saved $95,000 by employing this technology. This building has received the largest cash outpay from the savings by design that the PG&E or PUCEC has ever given. We received a check in the amount of our owner's share was $108,000. The design group received $48,000. I took advantage of that the 50% self-generation payment for the photovoltaics. And we went and built the photovoltaic system on the building. The total process has a 27.1% rate of return for the invested money. This building has been validated to be 42% Title 24, 1998, and
42%
below Title 24. And you know, I can tell you all the good stuff about CO2, you know, and SO and number of trees and cars and all the stuff that we've done by employing the PV technology. I'm happier with the environment and the space than any other space on the campus. The people in residence there are extremely happy with it. I mean, people that came from other places, even Stevenson and Darwin, into the building as their place of residence, just are amazed by how fresh and the atmosphere is in the space. I don't know if any of you have classes in there. Feedback's wonderful. We haven't heard anything. I personally haven't, and I would be the one that would be contacted. Again, it's Sonoma State University Salazar Hall, and we were able to do it here. After we get it analyzed, hopefully this technology will move out. It will become the mainstream technology.
What about some of the other products that were used on the interior that affect the interior quality, like paint and carpet and cabinets? And
you know, a real funny thing about Conklin Aikman carpet? 90%, yeah, 90% of their product now is clean. You're finding, you know, you got Title 24. The new Title 24 standards for VOC and finishes inside of a building are amazing. They're going to get even better with 2005. You know, we don't have an indoor air quality problem. Remember, 100% in, 100% out. So from the day I cranked this up, which was 6 to 8 weeks before they were done, or even had started painting in most instances, this building was operating. So there was no latent fumes in the building, no, you know, nothing off-gassing. None of the materials we used would off-gas anyway. Anyone else? Excuse me. I'm going to say there's a technical handout out of here. The building has been awarded the Regional Division 10 ASHRAE Technology Award for 2003, and we are a contender for the International Technology Award with ASHRAE for 2004. There's a handout up here that covers part of the slideshow, as well as the ASHRAE submittal, which goes into all the engineering that went on and further explains it to you. From this slide, you can get those ASHRAE chapters if you're more interested in the technology we employ. I didn't include any of the life cycle cost analysis sheets or any of that. That's a little deep. Yes?
When are you going to get a website up where we can access all this information?
You know, I'll say it one more time. I'm an engineer. Those two guys right there are guilty. Those two. It's their laboratory. When I get done getting all my analytical data, I'll give them the web. They can do whatever they want. I got enough computing power sitting in a control room over there. If they want to do it, I'm more than willing to let them.
And you had said that there was a $45,000 a year savings that included the PV system.
Right. Yeah.
And if you had just remained on the grid,
right,
what would your savings have been?
If I would have remained on the grid, I'd have had none. I would have had very little.
So,
because I would have been operating a new building in peak demand. Understand, this $45,000 is over the existing utility charges, is what I'm telling you. The whole photovoltaic that was installed up there is $234,000 out of our pocket. We annualized the $45,000 a year. That's a pretty good rate of return. You know? And remember, that goes on for 25 years. That $45,000 is in $2001 dollars, not $2004 dollars.
So there's nothing that takes as much power this indirect direct system as it would take to power a standard breathing system?
No, we're talking fans. We haven't gotten into the 414 tons of mechanical cooling that this is offset. I mean, it's just a given. It's gone.
But when you said you wouldn't have gotten any savings without EV, can I just explain that?
Well, no, I would have gotten a lot of savings, all right? But when I annualize the investment upon a return basis of, well, how much do I have in this? And how long is it going to take me to get out till I really see it? Okay? I only have $45,000 coming today, all right, based on $2001 dollars. When I pay down the $234, my whole window looks different. Because I hope to take and reanalyze this versus cost energy. This is not this actual number is based off the 42% below Title 24 plus.
So what you're saying is in 5 years you paid off the photovoltaic cell?
I've paid everything off.
Everything?
Every energy efficient measure that went into the building will be paid off. T5 lighting, the Loi Glazing, the daylighting additions, the addition of the lighting control. This building will pay out. Then we'll know.
So after 5 years, and you'll have to replace the photovoltaic in 25 years?
Yeah.
So you have 20 years.
Yeah. Yes.
Did you analyze the payback of the photovoltaic system alone, separate from the other
Yes.
features? And what sort of
7.8.
7.8 years?
Mm-hmm.
That sounds really short compared to other studies that I've seen.
But then nobody had $106,000 in their bank, like I did.
Oh, so that's including the money that you got from the savings by design.
Yes. You see, Rosenfeld at the public utility, Art Rosenfeld, I don't know. Okay, somebody I've met along my travels. In fact, Sasha and I were speaking to the UC people, and he was there at this meeting, and we did a little presentation where I was just talking about coupling incentives for alternatives, and I spoke about that. What we had done here about why the photovoltaic became such an advantageous thing for us to do is because we had this extra $106,000.
What if you did, is what I'm saying, if you just looked at, say you
I didn't analyze that. I didn't. No.
Most, real numbers that I've seen.
Large-scale real numbers are out there. They're 12 to 14 years.
I would say more like 30.
Well, but see, again, you can start from two places. You can start from the numbers relative without the rebate and the numbers with the rebate. And if you choose to use the numbers with the rebate, that's why it's there. It brings it back in most instances, to that teetering on the 10-year. Yeah. I mean, I deal in watts per square foot, and watts per dollar. And I mean, that's the way I'm looking at photovoltaics now. It's a commodity to me. I'll go to SHOT, I'll go to Powerlight, I'll go to BP, and I'll go, you want to do a system? How much? Give me your best deal. I don't care who you are. I have no allegiance. I'm in the state. I'm here to get the best bang for the taxpayer's dollar and show the taxpayer what we can do with their dollar. And have good financial accounting of their dollar on real solid numbers so that wall of resistance we've all been running up against, gets broken down. Yes, I'm on it.
I was going to add that one of the things that happens in financial analysis of PVs is they don't take into account some of the things that Keith did, which is taking a look at what peak load you're displacing and peak charges you're offsetting. And so if you don't start to include those, if you don't have a sophisticated model, then you get into 30 years. But if you really look at what you're offsetting, if you're reducing your peak demand 100% of the time, that's a huge part of the equation. So I think that's important to recognize, how it's being analyzed and what's being improved.
Well, yes.
Question on that whole life cycle cost issue is another number that really affects a lot is the energy escalation numbers.
Right.
You look at what the DOE is putting out for energy, escalation in the next 10 or 15 years. It's like 1% or something a year.
Well, it's based on cost of funds. And if you can believe the Ouija boards coming out of Washington, I need to stop. They're recording me.
About what's up for the Rec Center and what's up for Darwin? What's that going to look like? And how is it the same? How's it different than what you thought Salazar?
Okay. As I mentioned about Salazar, there was those 36 hours where analysis proved that the indirect direct could not support it. Well, what we did at the Rec Center, as opposed to paying the price to put a connection to the central distributed chill water system on a campus, I came up with an idea of using rotary scroll DX compressors, placing a very small refrigerated coil in the supply air stream, and using the scavenger air leaving the air handler as my condensing airstream. The fin spaces of these coils are so great that I impose a negligible energy penalty upon the moving of the air through the air handler. And I get that extra 5-6 tons of cooling that I'm going to need just to take the top off of this process. So we've employed that. I came up with this idea in 1991, or 2001. I was back at Virginia Tech working on the final design of the air handlers for Salazar with some friends, and we came up with this novel idea. One of the people that was present then is my cohort and running mate, Todd Felder at Sandia National Energy Labs in Livermore. And they bought one. They have one sitting down there on their maintenance building running, and we have the guys across the street, we call them, at Lawrence Livermore LB&L, doing an analysis on it. And this is proving to be very successful also. The Recreation Center is a multifaceted, naturally ventilated, direct evaporative cooled building, indirect direct evaporative cooled building with onboard refrigeration. Hopes and plans are to put a sizable photovoltaic array on the roof of these buildings, being driven more by a financial concern and the current enrollment environment and everything else going on here. And that building is 51% better than Title 24, 2001, folks. We worked with the student union group. Their desire was to have a building that was capable of providing them with some form of LEED accreditation. I worked with all of my cohorts, and I did an analysis, and the building was 63 points, which is a platinum building, without spending a whole bunch of money. And a decision had to be made about the financial investment of state dollars to hang a plaque on a building. And to current date, the decision just recently was reached that we would not seek at this time a LEED's accreditation for new construction. What is available through LEED now is the possibility of doing what's known as EB, or existing buildings, and that would be our best avenue to pursue. So the building will be hopefully as successful as Salazar, if not more successful. It presents a whole bunch more challenges because of its hours of operation, the different loading that takes place in the building, the different usages. On to Darwin Hall, we're partners with the Labs for the 21st Century. It's a group of people that are trying to design laboratory buildings now which are energy efficient. The most inefficient buildings operating today are laboratory buildings. If you've been in a science classroom and you walk by and look at one of those fume hoods, that one fume hood consumes more energy on average than 4 1,200 square foot residences do in a year. Okay? That's just a novel thing to remember. Darwin Hall has 61 of them in right now. So you can see, science buildings are energy hogs. So what we do is we design variable airflow volume technologies. We design indirect direct evaporative processes into them. We design lighting controls. We design hoods that go down to minimum flows if you're not standing in front of them. Then you start to life cycle cost all this into the equation. And you come up and you analyze what is the best technology to be employed to reach your efficiency goals. Darwin's in the preliminary, we're in the design development stage right now. We will be in this stage until August, I think, before we will see something that looks anything like a preliminary construction drawing. We're hoping to cover all the bases. We have a lot of partners. Like I said, we've got PG&E in here with me. They have Rumsey Engineers, their energy engineering group. We have Lawrence Livermore Berkeley's people from the Labs for the 21st Century, and a lot of other offers of people to come help us. So we're again going to hope to build a third real fine building here on campus. Now for the news flash. I have been able to employ indirect direct evaporative technology at the Green Performing Arts Center, Music Center. Don't worry about it, Rocky. I took the 275-ton chiller down to 75 tons, guys, by employing this technology. I'm pretty stoked about it. You know, there's a lot of things people are saying about that building, but, you know, there is that separation that exists between the arts and the rest of the world. And I've been able to apply a little bit of my real world into that, and I can satisfy their needs. And, you know, because I couldn't do much with the adjustable acoustics in the performance hall, gang. I couldn't do much with the exotic and elaborate lighting schemes that you need to put on a performance. I couldn't do anything with them. They have to be what they have to be. So what's the best thing I could do? I could approach it from how I could have the best impact, and that was through the HVAC in the building. And hopefully, we'll be better for it. Please. Yeah.
On these two new buildings in campus that you're working with,
Yeah.
are you going to have chilled water coils in either one of them?
No. We're done with the central distributed chilled water loop. I have been promised that there's a possibility, if we all vote for 55, that the bond measure that's out, that I might get a first pass at redoing the central distributed utility systems here on campus. So let's just see where that goes. Yes.
It seems like you put most of the majority of the effort into doing the analysis of the cooling side of the equation. Is that because you looked at the heating side and then decided that you don't get as much bang for the buck there? Or just curious if you looked at some of the solar thermal space heating solutions.
No. Well, I didn't go from on the pool. Let me talk about the Loi project of residence housing over here. This is the largest hydronic floored heating complex in Northern California. Short of large industrial warehouses in the Midwest, nowhere is there this many square feet under hydronic heating in one complex. My energy consumption to natural gas is 50% on a residence basis to the Sauvignon Village, which is forced air ventilated heating. I'm pretty happy with that one too. I ain't got time to study it, guys. Just ain't got time. I just go read the meters, count heads, and that's what it's all about over there. But we did the analysis and said this is where we're going. And the second phase is identically the same. It's all hydronic radiant floor heat, 3-story buildings. Novel approach to that is that in those buildings there are 600,000 BTUs of gas being fired into small boilers to heat each one of those buildings. Over in the Sauvignon Village, same number of people. You have these 50,000 BTU forced gas furnaces for every 4 students. So I'm telling you right now, I had to find a way. Philosophically, I can't do much about the prices of energy. I have to learn how to operate within their constraints. And efficiency is the answer. Yes?
Have you ever heard of running cool water in the hydronic slabs to use them to cool the buildings in the cooling season?
Yeah, it's a process that's employed not only through doing a dual. We used to call them dual pipe systems. In fact, it was done a lot in the HVAC industry and high-rise building back in the 60s, where your chill water and hot water would share the same coils and same piping in a building. With hydronic, it's highly possible to do that. The treatment of the water streams can be asimilar. It would just require a mechanical means to cool it. There's numerous technologies out. Chilled beam, radiant panel, where in a more passive form of cooling. I've just recently come across this thing in Europe they do called air floor, where you create a honeycomb in the floor and you blow tempered air through it, and it acts as a radiant system. And the ventilation component is the only you take the ventilation component and discharge it up along the perimeter or against a window in the space. Used a lot in cathedrals. The Germans have used it with ground source heat pumps I have pretty much stayed here at Sonoma State design-wise. I've assisted in some other buildings, but pretty much as the challenges presented themselves here, I've chosen to dedicate to them. I personally think, we're living in this artificially controlled energy environment, and energy really costs more than what you're paying for it today. I think it's being held down artificially. I personally think we need to move towards more wind power, or a combination of different alternative sources to feed any one location. My boss thought it was great fun that I was going to put a windmill on top of Darwin. No. Something about that 50-foot wingspan he couldn't get behind. Yeah, they do. Yeah, I know. Yeah, but there's not enough roof space up there once we put the air handlers up there and all that new ventilation that the code's requiring us to do in the building. There won't be enough roof space. It's the limitation with high-rise buildings. Okay. You want to take a break, Rock? I do.
Well, yeah, I think it sounds like maybe most of the questions got asked for the course of the presentation.
Right.
I think what might make the most sense is we'll just call it a formal conclusion to the forum today. Make sure the people that I passed the sign-up sheet, so some folks over there may be missing it. But then, of course, invite anybody that has more technical questions or any other questions to come on up and bug Keith. He's got technical reports and get into gory details, but if you're not having time, then I say see you next week. Next month is alumni